Hi everyone, welcome to my garden for the third practical now, isn't it? Doing pendulums today. So I've set up this pendulum and hopefully you'll be able to set up a pendulum. I'll just show you how I've set my pendulum up. Okay, so I've got the rubber bung and the string, and I've actually tied it to the top of this like parasol umbrella-y thing. However you want to attach yours is up to you. There's plenty of options really. You've got some gaffer tape as well you could stick it to. I guess if I was thinking what I've got around here, I could do it in the doorway of this shed look. I could just stick it to that somehow with some gaffer tape, or maybe kind of some inside options. You've also got doorways inside, haven't you? And other things that you could potentially tie it to, shelves, fittings that are fairly high up. This, I've managed to get it so that it's 1.5 meters long. You might only get one that's 1 meter long, but that's fine. So the longest we want it is maybe 1.5 meters or 1 meter. Okay, so the next thing we're going to do is actually a bit of trig, because the equation for a pendulum depends on the small angle approximation. So we want to make sure when we're displacing this pendulum that we're going to displace it by 10 degrees or less about. So this pendulum I'm going to change the length of, and the shortest pendulum I'm going to go in my experiment is 1 meter, because I started at 1.5. If you started at 1 meter because you didn't have as much space as me, then you're going to use half a meter for your length of a pendulum, and then we'll just, you could stand here with a protractor and just make sure that it's less than 10 degrees, but I think it's a bit easier to do some trig and then work out a horizontal displacement. So I have a right angle here for our triangle. So I've done tan of 10, and I've times that by the minimum length of my pendulums times by 1, and I've got 17 centimeters is the maximum that I can displace this by. So that's what I'm going to do. When you've got this set up, then you can just have a play about with it, change the length, and you can see that the time period will be dependent on the length. So when we're measuring this time period properly, we're going to measure 20, and we're going to divide our time that we get by 20. But you can see here that the time period is going to be affected by the length of the pendulum, just by doing a couple of preliminary experiments. There we go, look. And so what we're going to do is we're going to investigate that. We're actually going to pretend that we don't know what the formula is, and we're going to investigate it in quite a rigorous way so that we can actually... Okay, so we know that the length is going to affect the time period, and I'm going to suggest to you a formula like they might do in paper 3, and we're going to see if we can prove it. So we're going to suggest that the time period is equal to A times the length of the pendulum to the power of B, where A is a constant and B is a power that we're going to raise L to. So in order to kind of prove this, we're going to need to draw a graph because we're going to do an experiment, and we're going to use our results to find A, and we're also and we're going to use our results to find B as well. So B, when we find B, it should be a half, because in the real formula it's the square root of L. So we're looking for B to be a half really in our results, but we might find that, we might not, depends. And A, we're looking for it to be 2 pi over the square root of G, which we'll check later on if this has kind of worked. So first up, we're going to take logs of both sides, and then I'd like you to get it into a form of y equals mx plus c, so that we can plot a graph.